Alright, so welcome to Lecture 10 of General Relativity. This is a short lecture, I hope, on classical field theory. I don't have too much to add here, really, to... oh, that's not true. I've got a ton to add here. Oh well. Let's get to it. So, the problem of classical field theory is to try to explain the dynamics of fields on space-time. Generically speaking, Carroll uses this phi I of x mu to denote, like, the phi I fields. So like each I gives you a different field, okay? And so this amounts to basically assigning a different parameter to each point in space-time, and for each field. So it's infinitely many variables, really, but infinitely more than we were talking about in the last lecture. Anyway, so we're going to use a variational principle to set up the calculus for these classical fields. So here, because you're not talking about just, you have to integrate. The way to capture this idea is to integrate a Lagrange density over space, and then that Lagrange density depends on the fields and the derivatives, and you integrate that over time to get the total action. And all of this said, we're just going to call this Lagrange density the Lagrangian because everybody else is doing it. All right, so and we'll vary the fields here. Vary the fields, and suppose that the variation of the action is 0 implies the equations of motions for the field. That's the idea, much like we did in the last lecture. Just now we've got more variables. And so when you look at the, Lagrangian plus the variation of Lagrangian, it should be something like what you get from, varying the fields, which is to replace phi I with phi I plus delta phi I, and the derivative with, plus the derivative of the variation. And essentially by Taylor expansion, this gives you to here. There's higher order things, but they're so small we don't care. And when you look at this, this tells us that the variation of L is just these two terms. All right, and then it's kind of the same song and dance as before. One of the big differences here, of course, is that I had to. There's a sum over mu going on here, and there's also a sum over I. So yeah. Yeah. So again, sum over I and sum over mu going on here, and but then we do the same thing we did before. We do the product rule. This is basically integration by parts. There's a total derivative term. This is a four-dimensional divergence of this term. You're assuming that the variation of the fields goes to 0 on the boundary of some region of space-time by the four-dimensional Stokes theorem, usually. There's actually a rather famous case in nuclear physics where this matters. The instantons. So the study of instanton physics involves things of this sort which cannot be neglected. So-called large gauge transformations, also part of the story. Anyway, that actually led to interesting mathematics as well in the 1980s and even to this day. First of all, the study of what are called Donaldson invariants, then later leading to the study of Seiberg-Witten theory, which is an ongoing problem. People are still working on the Seiberg-Witten equations and how to deal with those. I have a student who went to grad school and ended up working on that stuff. I'm deeply jealous of his work. I would love to understand it more. But anyway, my point to you is this is this usually, actually when it's not true, is actually very interesting. But anyway, getting back to what we're talking about right now, we have this minus that. You can factor out the variation, and since this holds for all possible variations, we see that we need this quantity right here to vanish for the Lagrangian, and that is, my friends, the Euler-Lagrange equations for classical field theory. So on space-time. Okay, so again, it all comes back to assuming that the fields are functions of space-time. So we get partial L partial with respect to the field, minus the sum over the derivatives of time and space here. This is a sum over that. Of the derivative of the Lagrange density with respect to the derivatives of the field. So this, you get one of these equations for each I, all right? So a nice simple example for us to cut our teeth on is the real scalar field in physics. That would be a problem in physics which involves this model would be the neutral pi meson. It's a scalar field. And anyway, so kinetic energy, 1/2 phi dot squared, gradient energy, 1/2 nabla phi squared, and then a potential energy v phi, all right? So you got your potential energy is a scalar function, so it's already a Lorentz invariant. However, the kinetic and the gradient terms, you got to combine them like this. In so doing, you make it into a Lorentz invariant. Notice the contraction of up-down indices that leads to the goodness of this expression in terms of Lorentz invariance. So in total, here's your Lagrangian. And what are the equations of motion here? Well, we take the partial derivative of L with respect to phi, we get minus dv d phi. We take the partial derivative of L with respect to the derivative of the field. And then you got to do a product rule like so. Product rule. And then this is Kronecker delta mu alpha, Kronecker delta nu alpha. Carroll's careful to put up-down indices here. I'm not, whatever. And anyway, so that leads me to these two terms are really the same if you look at it from the bigger picture here. If I replace nu and relabel the sum over nu and mu with respectively mu goes to nu and nu goes to mu, and then I use the symmetry of the eta mu nu, then this term becomes that term. And so you get two of them. The 2.5 cancels, you're left with that. Then this Kronecker delta changes the mu to an alpha, and then you get this, right? Okay, and to be, if you wanted to go further, you could even write that. I don't think he does, but you could, if you wanted to play these games, you could write that as minus partial alpha phi. Okay, that is not wrong. You could do that as well. You can raise the index on the derivative. That is something you can do. And once you've got that, leads us to the Lagrange equations for this real scalar field just being this, but in detail that is dv d phi, and then partial mu of this guy. All right, but that guy is, well, now I'm doing it. So I'm raising the nu to a mu. All right, and so minus minus gives me plus. So you got the contraction of the derivative, the covariant derivative with the contravariant derivative, if you want to use that language. And this guy is box. So you get box phi minus dv d phi. This box is called the D'Alembert. Specifically, it's the second order differential operator, which is like nabla squared minus the time derivative squared. So that's, the box is a joke. It's four-dimensional. It's the four-dimensional gradient. You get it? Ha ha ha. Funny. So if you're in five dimensions, you have to use a pentagon. Anyway, there you go. Welcome to my introduction to grad school meet and greet with some of the theoretical professors. It was fun. Anyway, if we're given v of phi is this, then, so in other words, if you get what's called the simple harmonic oscillator potential, then this equation becomes box phi minus m squared phi equal to 0. This is the famed Klein-Gordon equation, so of which there have been many things written. It has nice solutions. It's a linear differential equation. It's got plane wave solutions, all kinds of good stuff. All right. Now, next up, electromagnetism from Lagrangian formalism. So we introduce a vector potential. What's a vector potential, you ask? Well, that's a good question, because it's definitely something you didn't see in your introductory course. So the vector potential, it's got the voltage and the what I usually call the vector potential. All right, so this is the potential, the four potential, you could call it. This is the scalar potential and the ordinary vector potential. In particular, B is the curl of the vector potential, and the electric field is minus the gradient of the voltage. And then there's this other term that you probably haven't heard about before, that's minus the time derivative of the vector potential. So you recover E and B inside the field strength. You can show that if you take this anti-symmetrized combination of partial derivatives of the vector potential, four vector potential, that reproduces the E's and B's of the previous lecture that we had. I don't think that's immediately obvious, and I've got more to say about it in a different formalism, so let's go on. Now he points out that if you replace the vector 4 potential with 4 potential plus the gradient derivative of a function on space-time, then even though you're changing the vector potential, you don't change the field strength, because when you shift by this, you end up, all that you pick up is this words partial nu lambda minus partial mu lambda. Partial derivatives commute, so that's 0, which is to say that the field strength is gauge invariant. This is the gauge transformation we're speaking of here. All right. So now Carroll also points out that if you look at the anti-symmetrization of partial mu f nu sigma, that's automatically true if we have the star equation up there, or at least the homogeneous Maxwell's equations come for free if we use the star formalism, you could say. So this is going to work out to 0 because the partial derivatives commute. I don't think that's immediately obvious. Like, each one of these is like 6 terms, so you got like 6 terms to write out, and then there's some cancellation of matching terms that comes from all that to be like 12 terms to write out. I don't feel like writing them. Because I think there's a better way to think about these. Let's talk about that for a couple pages. If you don't mind, I'm going to digress from Carroll here for a bit. And so the way I like to think about this stuff, if I'm going to think about it, is with differential forms. And so, like, the differential forms way of thinking about this, one of the things I noticed is, and I'm not sure if Carroll is being careful here and he has a different convention, or if it's just an oversight, but in Griffith's Electromagnetics book, like the one I was showing you back in lecture 8, this guy, this one, he defines the vector potential with an upper mu, the voltage vector potential, like the one-form potential. And if you do that when you lower the index to get the potential one form, that picks a minus up on the voltage. And of course Griffiths doesn't use phi for the voltage, he uses V for voltage because, it's Griffiths. And whatever. So here's your potential one form, it's a differential one form. And here omega A is the work form, it's this A1 dx plus A2 dy plus A3 dz. So with that, you can calculate the exterior derivative of A, which will be minus d phi wedge dt plus the derivative of omega A. And so here there are time derivatives and also spatial derivatives, which appear, and it works out to this. This is the flux form of the curl. The flux form is this guy. And so almost out of time here, unfortunately. Let's see here. So we got the, you put these two things together, you get that, but that's exactly the magnetic field, the electric field rather, and that's exactly the magnetic field. So lo and behold, the exterior derivative of the one form is got the electric field and the magnetic field appearing like this. So you can use this actually to define F. You could, from this way of thinking, I would define F with this, I would say, well, the F is a 2 form on space-time, and I would actually let this be its definition. But we are, of course, already have a definition for F, and anyway, you can, if you go back and look at page 2 in lecture 8, where I lowered the indices on the field strength, you'll see that this matches up, I think. listen, I could be off by some signs here or something. I'm not being super careful. I'm trying to be careful, but anyway. So f is dA. Well, then df is ddA, but d squared is 0. And so this is automatically 0 from, like, calculus of differential forms. But on the flip side of things, df is d of this, and that works out to the flux of the curl of E, wedge dt, plus the flux of the derivative of b with respect to t, wedge dt, plus the divergence of b times dx, wedge dy, wedge dz, which implies then that curl of E plus partial b partial t is 0, and that del dot b is 0. But of course, these are exactly the homogeneous Maxwell's equations. So, that, to me, that's how this stuff fits together. I mean, you can work in the tensor formalism that Carroll does, but I don't know. So understandably, I mean, like, a lot of physics students don't have the background that I'm using right here. I'm using this because I know that a lot of people who are watching this have also seen my, like, differential geometry course, and so or maybe the end of my Calculus 3 course, so you know how differential forms work a little bit. If you don't, you can, if you email me or something, I'll point you to where to look. But anyway, so the gauge transformation in this language just looks like a plus d lambda. So then, like, f transforms to a plus d lambda, which is dA plus d squared lambda, which is f again. So, like, it's just everything gets easier in this language. To complete the story, though, so yes, we have to introduce something called Hodge duality, which flips p to n minus p forms. I'm not being terribly careful here, but, like, dt Hodge duals either plus or minus dx wedge dy wedge dz. The Hodge dual of dx wedge dy is dt wedge dz, and this one's like that. I don't know if it's plus or minus. It depends on your conventions. All right. I'm more certain that the Hodge dual of this has to be that, if I'm right about other things. So, like, the exterior derivative of the Hodge dual is it d omega b wedge dt minus d phi, and through essentially the same calculation I just went through on the other page, that gives us this term, this term, this term, and this term, which then gives us the flux form of the curl of b minus partial e partial t minus the divergence of E. And we should think that that's the Hodge dual of the current one form. The current one form would be rho dt plus omega j. Its Hodge dual apparently is minus rho dx wedge dy wedge dz, and plus the flux of the current density wedge dt. So I guess if you believe this, you probably want to put a minus for the first one for what it's worth. But anyway, my point to you is just this. We can rewrite Maxwell's equations as df equal to 0 for the homogeneous ones, and d Hodge dual f equal to Hodge dual j. This captures the inhomogeneous Maxwell's equations, namely Gauss's law and Ampere's law with Maxwell's correction. So, I think if you're going to talk about Maxwell's equations on space-time, this is the way to do it. And really, it's not different than what Carroll's doing. I'm just making use of the differential forms way of looking at the tensor altogether rather than without coordinates. I mean, some people would say what I was just writing was coordinate-free. Well, yeah, it's not quite right. It's not quite coordinate-free. I mean, I should say this. These are coordinate-free. This is very much not coordinate-free, okay? Anyway, so getting back to Carroll, the Lagrangian of electromagnetism is minus 1/4 f mu nu plus a mu j mu, where this is the current one form and the current. So this is the forecurrent, which includes ordinary charge density and the current density. This is the for potential, which includes the ordinary voltage as well as the vector potential. And these are the field strengths that we've been talking about. So the Euler-Lagrange equation for the fields, which in this case are the one-form fields, are just these. And so this page here just calculates that, all right? So, like, first of all, differentiate with respect to the a nu, it just pops out j nu. All right, great. And there's kind of an ugly calculation here. trying to, sorry guys, I'm kind of out of time, so I had to try to wrap this up here. So this, I can relabel the dummies like so, and then pull the index alpha beta down to rho sigma here like that. Then I take the derivative of f alpha beta with respect to mu alpha, partial mu a nu, which gives me this, which gives me this pair of Kroneckers. And then I use that identity when I'm differentiating this because I got a product rule. So I get that delta and that delta, which then multiplying this out gives me all this stuff, which then, if you look at this, we're taking nu, the rho is summed over here, so that takes the that rho and raises it to a mu, and the sigma gets raised to a nu. This one, the sum over rho, raises the first one to a nu. The sum over sigma raises the second one to a mu. And similar comments apply here and here. So you got this plus, and so, but it's antisymmetric, so you can just write 4f mu nu. So that's the partial derivative of the contraction of the field tensor with itself with respect to the derivative of the one-form field, the four potential. And so lo and behold, partial L, partial the derivative of a nu just gives you minus f mu nu. The 4 is gone because remember there was a minus quarter in here, so that minus quarter and this 4 cancel to just give you a minus. And then, oh man, really poor planning on my part. Then this right here, the first term is just j nu, and the second term is minus partial mu f mu nu. But then you take care of the minuses, bring it to the other side, and then you can commute to f mu nu is minus f nu mu, which gives us this, which of course is the same as lecture 8. So there it is. Now, of course, you know, obviously, guys, where on earth did this come from? Like, that is not explained. If you'd like to read a leisurely, somewhat leisurely exposition on how to come up with this Lagrangian from sort of like somewhat interesting base principles, if you look at Ryder's quantum field theory, if you look at Ryder's quantum field theory, either first or second edition, I don't think it matters. He's got about 3 pages where he walks through a variational Lagrangian for a complex scalar field, and then couples it to a local gauge transformation, and then shows how that local gauge transformation necessitates the introduction of a vector potential, which then necessitates the introduction of a field strength in order to maintain the gauge invariance, the proper properties, symmetry properties for the Lagrangian. It's really quite striking. The argument goes back to Weil. I think it's an old argument from like 1929, I think, and it ultimately led to a lot of the modern physics that we love. But anyway, so finally, just to summarize here, the energy. Carroll ends by stating the energy momentum tensors for the scalar field is this, the energy momentum tensor for the electromagnetic field is that. And these are not derived. He mentions, I think there's some procedure in chapter 4 these are going to be derived from. In the meantime, you could show that these are conserved if you apply the equations of motions. Those are some pretty good calculations to try your hand at. I think that's like problem 12. I'll probably assign that because I think that'd be good tensor calculus for you to kind of like churn over. So basically you can show that the conservation, that these stress energy tensors are conserved if you apply the equations of motion. And then he ends with just some nice comments about standard model physics. So as Carroll talks about, and I'm sure you've heard before, there are gauge fields, Higgs fields, and fermions. The gauge fields describe how the 4 forces are media propagated. You have strong force, weak force, electromagnetic force, and then gravity. Gravity, I would say, is kind of an odd man out here. That's not really part of the standard model, let's say. I don't know if it is, or I mean, I'm not sure how you define. Depends on how people define, but to me, this is kind of a little bit different because we don't have a proper quantum theory of gravity, as far as I know. Strong force, weak force, electromagnetic force, the force-carrying particles are gluons, the W plus minus and Z naught bosons, and the, of course, photon for electromagnetic force. Turns out that the electric and the weak force can be combined at a higher energy into the electroweak force, and so there's some kind of interesting story there about how that higher energy physics produces the photon in these W plus minus and Z naught bosons as the symmetry breaks. I think that also feeds into the story of the Higgs boson. The Higgs boson explains how things get mass, so you know the W plus minus and Z naught bosons have mass. That means that they're very short range, whereas the photon is massless, which means it has infinite range. Gluons are also massive, so they have short range. These are all spin 1. That's spin 2. Higgs boson, spin 0. It's a scalar field. The electron, neutrinos, and quarks are spin 1/2. Now, you say, well, what's spin? Well, we're not going to explain in this book, but spin describes how the elementary particle couples to magnetic fields. It means a very specific thing about how it's the kind of representation that it carries. And anyway, all these fields carry matrix representations of the standard model symmetry group. And so like color, weak, and electric, I think. I don't remember exactly, but I think this is somehow, it's just SU2 at like higher energies, and it somehow parses into this at the lower energies. But anyway, don't have the details for you here. I will say this: quantum mechanics, well, quantum field theory allows for interpretation of low energy physics as an effective field theory. So somehow the high energy physics processes renormalize into the coupling constants at the lower energy. So in short, we find that there's decoupling of physics at different energy regimes, which means that we were successful at studying like electronic physics without knowing nuclear physics. And we were it's like each, I would say that the universe has been created in such a way that us humans can study physics at different energy regimes without having a complete mastery of the next higher level energy regime. Now, I'm sure some people would look at it through some sort of anthropomorphic principle, but to me it just is evidence of divine providence. But in any event, the decoupling is not in Carroll. This is from another book I've read bits of, but it's kind of ties into what he talks about renormalization. Anyway, just sufficient to say that there's tons of ideas in quantum field theory you need to digest to properly get from the classical field theory I've described in this lecture a little bit to actual how we describe physics. Anyway, where we're headed is general relativity, and there the metric tensor is actually the dynamic field of the theory. So the metric tensor for gravity plays the role that like the A mu did. So here the dynamical field was the 4 potential, and which is kind of funny because in some sense it's unobservable. Is the metric tensor unobservable? Unobservable is too strong a term, but there's a degeneracy in how it can be interpreted from observations, right? Because there's a gauge freedom there. So anyway, the analog to that would be the metric tensor for GR. That's at least one way you can look at it. So anyway, I think that's it for chapter 1 in Carroll. So next up, I think, is fun calculus on curved spaces and things. And anyway, thanks guys.